Hey folks, welcome to Gas Laws, first podcast on gas laws. This one, what we're going to talk about is this one is going to be all an introduction to what's going on. It's going to give you some of the logic behind gas laws. So we're going to try and give you an idea of what's coming. Okay. This is a beautiful picture of a mountain in the winter, and what we're looking at is the air. Now, what in the world makes up air? What are the components that make up air? Well, obviously you know some of them. You know it's oxygen, because obviously you breathe in oxygen and we need that to live. And you should know by now that most of it is nitrogen. The biggest component of air is nitrogen. And of course, when we breathe in oxygen, we breathe out carbon dioxide. So there's carbon dioxide in the air as well. Of course, there are many, many, many other things in air. Right? So if we actually look at what is in air, here's a list of lots of things that are in air, and frankly what you need to notice is you need to notice the top two. The top two are nitrogen and oxygen, and between the two of them they make up about 99% of air. Alright, is nitrogen and oxygen. And we tend to think that, most people think that oxygen is the major component, but actually it's not. Oxygen is only about 21%, whereas nitrogen is the biggest component of air. Now, here's a picture of Mauna Kea. This is one of the volcanoes out in Hawaii. And when you look at it, does air have a color? Obviously, Mauna Kea has a color, but does air have a color? No, air is colorless. It's clear. You can see right through it. So, no, it does not have a color. How about, does it have an odor? Here's another one of the volcanoes in Hawaii, Mauna Loa. Does air have an odor? Well, no, you might say, well, sometimes it does. Well, actually, sometimes it's transporting an odor. For example, if you have someone who's wearing perfume near you, you will smell the perfume. But that's not the air that you're smelling, that's the perfume. So air itself, just pure nitrogen and oxygen, has no smell at all. So what is transported through the air? We already talked about one, which was perfume. So that's an example. So pause the video and think about it. What would be transported through the air? No, I'm not kidding. Pause the video. Give it some thought. Okay. So one thing we mentioned already was smells. And I think this is kind of cool. This is a hotel that's outside of Boston. And right here is a restaurant. It happens to be Howard Johnson's, or at least it used to be. And what they do is instead of pumping all of their exhaust from their fryers and their hamburger stuff all up, they actually do it right down into this tunnel. Right, so when you're driving by here and you're going along and you're driving through this tunnel and you smell all of a sudden hamburgers, you say, oh, gee, I'm hungry. Wouldn't it be nice to have a hamburger? So you come over here, and right here there's an exit ramp, and you get off the exit ramp and you drive right past and you go right back in and you can have some lunch. So yeah, that actually is intentional. So obviously smells are transported through the air. Energy, like electricity, is transported through the air. So here's an example of a lightning strike in New York City. Energy is transported through the air. Heat is transported through the air. Now, realize that you say, well, it's also transmitted through outer space. Well, no, it's not. Light is transmitted through outer space. So we get heat from the sun because of the sun's infrared radiation, which if you go back, way back to stuff we've talked about before, that's light, that's not heat. Heat here is transmitted through the air. You can get right up next to that fire and it's pretty toasty warm. Alright? The same thing with sound. Sound is not transmitted through space. Sound is transmitted through a medium, and our medium here is air. Alright, so now we're going to kind of shift gears here a little bit and talk about the physical properties of gases. Now, a lot of these guys you already know about, but you've never thought about them in terms of chemistry before. So let's think about them in terms of chemistry and what's actually going on at the molecular level. That's kind of where we're going. So gases are compressible. When you think about it, water doesn't compress well. Solids, if you hold a rock in your hand and you squeeze it, you're not going to be able to compress it, but we compress air all the time, and we put it in bicycle tires or car tires or whatever. So air is compressible. We also put it inside tanks so scuba divers can go underwater. So air is very compressible, whereas liquids and solids are not. They fill containers completely. So let's say, for example, I drop a penny into this Coca-Cola bottle right here. Well, the penny's going to sit at the bottom. It does not fill the container completely. Or let's say I put some liquid in here. Well, the liquid's going to be at the bottom. It's not going to fill the container completely. But when you think about this container, it has air up here, it has air down here, it has air all the way at the bottom, and there's the same amount of air. If I take a cubic centimeter or a particular spot of space down here, and I do the same thing up here, it's going to have exactly, if I use the same volume, it's going to have exactly the same amount of air in it. Okay, so it fills the container completely. Now, physical properties of gases. You understand that it can move quickly. For example, in a hurricane, you could say, well, gases move very quickly, but you really don't understand how fast the air is moving. When all of the molecules are kind of moving in one direction, yeah, we create some wind, all right? But each molecule itself is moving much, 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 much faster than you think it is. In fact, it's moving over 1,000 miles an hour. And we're going to talk about that in a couple of minutes. It's moving extremely quickly. Now, gases do exert pressure on objects, and you can do this at home. You can take a bottle, and you can put a balloon on top of it, and stick it in some water. Nothing's going to happen. But if you take that water and you heat it up, you'll notice there's some flames down here. If you heat that water up, right, that's going to make the molecules, that's going to heat up the molecules inside the bottle. Well, the molecules in the bottle start moving faster. And when they start moving faster, they have nowhere to go. So they go and they start going into this balloon, and they start pushing out on the insides of this balloon. We call that pressure. So pressure is the act of all of these molecules pushing against the inside of the balloon. And so they pump the balloon up, essentially. So there's more pressure inside a heated bottle than there is in a regular one. And that's because the molecules are moving faster. So pressure is clearly dependent upon temperature. Right, so you can actually try this at home. Here's a picture of one where you could actually try it at home, see what it looks like. All right, when you are testing your air pressure in a car, like this gentleman is doing over here, he's testing the air pressure. And this is telling how many pounds per square inch he has a pressure. Pounds per square inch. Gee, that means force per unit area. Yeah, he's testing the air pressure inside his tires. Now, you're supposed to do that before you start driving them, because the tires are going to be cold. And that's important. You don't want to test it when it's hot, because your pressure will change. And you'll see how that works in a little while. All right. Another physical property of a gas is that all gases have mass. And some are very light. For example, these balloons are full of helium, and that's why they can lift this person up off the ground. But some gases are heavier, like nitrogen or oxygen. Now, remember that if you have a particular amount of space where you have a gas, right, 1 mole of it, for example, of helium is going to weigh 4 grams, whereas 1 mole of O2 is going to weigh 32 grams. And they're both going to take up 22.4 liters at standard temperature and pressure. So your density of helium is going to be much less than your density of oxygen. But they all have mass, and we have to remember that. Hopefully I'll be able to put a video in here about the mass of a gas. If not, I'll show you where it is.
Here are 5 of the 6 noble gases: helium, neon, argon, krypton, and xenon. They're all colourless and transparent. Krypton and xenon form compounds only with difficulty. Helium, neon, and argon don't form compounds at all. As we descend the group in the periodic table, the atomic number and the relative atomic mass increases. The gases get denser. Helium is lighter than air. Neon is just lighter. Argon and krypton, I've just got to unstick these from the anchorage for a moment. Argon and krypton are both heavier than air. And xenon is the heaviest of the lot. You've heard of a lead balloon? Well, this is it.
All right. You all know that molar volume at STP is 22.4 liters. Now, I have this box here with a football and a soccer ball and stuff, so you can get a sense of the size of the box. If you ask me in class, you ask Mrs. Sherman in class, we'll be happy to show you a box that is, in fact, 22.4 liters. You should be able to kind of conceptualize that because that's about 11 2-liter bottles. Okay? So if you think of soda bottles, that's going to be about 11 2-liter bottles, okay, in size. Really, though, can all gases take up 22.4 liters at standard temperature and pressure? If I have a dozen golf balls or a dozen donuts or a dozen eggs or a dozen basketballs, they take up a different amount of room. So how in the world can all gas molecules take up 22.4 liters? That just doesn't make sense. Well, yeah, it does. And here's how it works. If you were to think of yourself at Lane Stadium at Virginia Tech, over here you've got a molecule of air, or a molecule of something. Let's say it's a molecule. The concept is I'm trying to give you a sense of scale. So let's say that I have a molecule over here that's the size of a pea. You all know what the size of a pea, right? Well, the next closest molecule in a gas is going to be about where I'm sitting. So the next closest one. So that's amazing that what is in between this molecule over here and where I'm standing over here? The answer is absolutely nothing. Let me say that again. Absolutely nothing. There's nothing in between these. There aren't other molecules of other things. If I have a gas, the gas molecules are really, 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 really far apart. So when you have a tiny gas molecule, there's all this empty space between it. So if you think about it, would it matter whether the thing over here was the size of a pea or the size of a golf ball or even a basketball? When you compare it to the one that's over here, they take up so little space, it really doesn't matter. So we think of the size of the gas molecules as essentially being negligible, that they don't matter. Okay, so all gases at standard temperature and pressure take up 22.4 liters of space because the majority of the space in there, 99.99% of it, is empty space. Empty space, what does that mean? It means there's nothing there. All right, so we're going to talk about kinetic molecular theory. These are pieces you need to be able to understand. Now, guys, I don't expect you to memorize the kinetic molecular theory. I do, on the other hand, expect you to be able to reason through these things so that they will make sense to you. All right, so what does kinetic mean? Well, you know it means energy of motion. And what does molecular mean? Well, that's a molecule. All right, so let's say we have hydrogen, oxygen. We have a water molecule. You know what a water molecule is, right? And then a theory means we really can't prove it because we can't see what it is, so we think this is what's going on. So this is how we explain our observations. So that's what the kinetic molecular theory is all about. It's all about gases and all about motion and the motion that the molecules are making in a gas. All right, so the first rule that we have is the motion of gas particles is rapid, meaning it's very fast. It's constant. It never stops. And it's random. We believe that gases are moving about 1,000 miles per hour. Now, we can sit down and we can do the math to do this. I'm not going to bother doing it in this podcast, but we can do the math because we know how to come up with velocity and mass and all those kinds of things. So we can figure out that gases at room temperature are moving about 1,000 miles an hour. Some faster, some slower, but that's about it. Okay? Now, we think about the motion of gas particles. How do we know that gas particles are moving? Well, when you walk into a movie theater, or an even better example might be someone in a classroom starts popping popcorn, and you're a couple of classrooms away. Can you smell it? Well, not immediately, but you can smell it pretty quickly. And you say, well, why is that? Well, it's because all of the air molecules are bouncing against each other, and they're knocking against the smell particle that's the popcorn. And that smell comes bouncing out into the hallway and then bouncing out into your room. If you were at the other side of a room, if you were at home, let's say, near the kitchen, and you were in the family room and somebody cut an orange in the kitchen, would you smell it? Probably. And you say, well, wait a minute, I've got air conditioning or heat running in my house, so that's moving the air. All right, well, let's go outside. About 6 in the morning. It's quiet, it's still, there's no wind at all, and there's a skunk in your yard. Will you smell it? You better believe it. Now, is there anything moving that air towards you? No. But all of the molecules of air are bouncing in every which way. They're all random directions. They're all going very, very fast. It's constant. Okay? And the smell of the skunk is being knocked around by all of these particles. And so as a result, it ends up at your nose, whether you like it or not. All right, another piece of kinetic molecular theory is that all collisions between particles of a gas are perfectly elastic. Now, for those of you who are taking economics, you know what that means. The bottom line is what it means is they don't lose energy. So think about what happens on a billiard table. You go and you whack into this 8-ball, and the 8-ball is going to hit this one, and this one's going to go flying off somewhere, and the 8-ball is going to go flying off somewhere. And anyway, they all go flying off in different directions. But they slow down, and then they stop. Why is that? Well, the air is slowing them down, so there's friction. And there's friction between the balls and the table felt, right? So they all slow down over time. All right, well, the belief is that for gas particles, the collisions between the gas are perfectly elastic, meaning they never lose any energy. They whack into one, they transfer some of their energy, all of their energy, whatever, but they just keep whacking into each other. And every time that happens, the energy is partially transferred, but it's never, ever, ever, ever lost. That's the belief of kinetic molecular theory, because if we did lose it, what would happen to all those air molecules? Well, all those air molecules would eventually sink. And when they eventually sank, they'd end up as a liquid on the ground. Now, guys, we can't breathe a liquid. Even if it's liquid oxygen, we can't breathe it. Okay? So it has to still be a gas. So if those things are losing energy, just like billiard balls would be losing energy, they'd eventually fall to the earth, fall on the floor, make a liquid, potentially make a solid, and we couldn't breathe it. That doesn't happen. So that tells us the molecules have to just keep on bouncing. They are elastic. All right. Another concept of the kinetic molecular theory is the particles in a gas are considered to be small, hard spheres with very insignificant volume. We were talking about earlier with the example of Lane Stadium, right? For a solid, the molecules are packed pretty closely together. For a liquid, they're still very closely together. But for a gas, they are far, far apart. In fact, if this were really drawn to scale, then there'd only be one molecule in this box. These other molecules would be way off somewhere else, okay? In fact, they'd be in the next room or the room after that, all right? Maybe outside your house, right? They're not going to be close at all. All right. So, but they're flying very, very fast. All right. But essentially, these things we view them as having no volume or an insignificant volume, so it does not matter to our calculations. Let me ask it again. What's in between these gas particles? Absolutely nothing. It's a vacuum. It is empty space. There's nothing in between the gas particles. So all of this space that you see, all this blue space or gray space or whatever it looks like to you, it's all empty. And that's why any gas can take up 22.4 liters at STP, is because the molecules are so far apart that almost everything is empty space. Now, if they all take up 22.4 liters, don't they all weigh the same? Well, no, they don't. We talked about this before. If we have something like helium, 22.4 liters of helium is going to weigh 4 grams, right? Because that's its molar mass. But neon, if we look at the periodic table, neon is heavier, and it has a mass of 20 grams per mole. So even though they take up the same amount of physical space, their masses are different. All right, so let's quickly review the kinetic molecular theory. We say that small particles, that they're all small particles and they all have mass. The distance between them is relatively large, meaning there's a lot of empty space in between them. They're in constant rapid motion and they never lose their energy. The collisions are perfectly elastic. Their energy depends on temperature. So you heat it up, they move faster. You cool it down, they move slower. And the molecules exert virtually no force on each other. They don't hold on to each other. If they did, then the collisions wouldn't be elastic. So they can't hold on to each other. They just have to bounce off each other when they hit. Okay? All right. That's it, folks. Please go off and do the worksheets. We'll see you in class. If you have questions, let us know. We'll be happy to help. Okay? Take care. Thanks. Bye-bye.